Okay, so I'm going to go back to our notes, and now what we can do with lenses and mirrors is we can also back up our ray trace with mathematics. Okay, so we can take the same information that we have from the ray trace and we can back it up mathematically. So what this equation does is it lets me figure out where an image will form. So S is our object distance from the lens or mirror. S prime is the image distance from the lens or mirror. And then F is the focal length of the lens or mirror. So 1 over the object distance plus 1 over the image distance equals 1 over the focal length. Okay, so that works for thin lenses or it works for mirrors equally well. Very easy mathematically if you get the signs right, but there are rules about the signs, and that's what's on the next page. So the object distance S for us 99% of the time is going to be a positive number. So it's positive if the incoming or the incident light and the object are on the same side. In other words, the light coming off the object and the object are on the same side of the lens mirror, which makes sense because it's coming off the object. Then that should be a positive number. So S should be positive most all the time. The only time you can ever get into something weird with S is if you have multiple lenses and mirrors, and sometimes when you work through those, what happens is the image formed by the first mirror or lens will be the object for the second lens, and sometimes it happens that that object form or that image forms on the wrong side, and you might get a negative number, but for us that's not going to happen usually. Now the image distance is going to be positive if the outgoing light actually forms the image. Okay, so the image distance will be positive for real images. So if the outgoing light forms the image, in other words, it converges to form the image, you have a real image, then that is a positive image distance. Virtual images will have a negative image distance because the outgoing light is on one side and the image is on the other side. Okay. Then the focal length is determined by the radius of curvature. Okay, the focal length, which is half the radius of curvature, will be positive if it's on the same side as the outgoing light for a mirror or a lens. Okay, and that's for the near focal point, or excuse me, the far focal point for a lens, far focal point. So in the case of the lenses, it was the biconvex lens is a positive focal length, and the biconcave lens is a negative focal length. For the mirrors, the concave mirror, the one that caved in, was a positive focal length, and the convex is a negative focal length. All right, so you can just kind of make a little chart to kind of remember that. Okay, now what I've done is I've worked a couple of problems to kind of show that. Okay, so I've also put these up on your Blackboard page as well. I've worked some examples. So we will pull up those and look at those. Okay, so I want to start with, I just picked some examples out of the different chapters to look at. So I want to start with one of those. So I want to start with chapter 18, number 44. Okay, and I tried to annotate these like I would be talking about them in class. So when you go back and look at them, you'll have a little bit more information. Okay, so problem 44 says a 2 centimeter tall object is 40 centimeters in front of a converging lens that has a 20 centimeter focal length. Okay, so a 2 centimeter tall object is 40 centimeters in front of a converging lens that has a 20 centimeter focal length. And in all these cases, we're supposed to calculate the image position and height. Okay, so the first thing I ask myself is, am I inside the focal length or outside? Well, if the focal length is 20 and I'm at 40, I'm outside the focal length. So I know it's going to be a converging system. It tells me it's a converging lens. So that tells me that the focal length is positive. Okay. So I'm going to use the thin lens equation. So 1 over F equals 1 over S plus 1 over S prime. So it's a 20 centimeter lens. So the focal length is positive. So 1 over 20 equals my object distance is 40. So 1 over 40 plus 1 over S prime. Now, I like to do fractions with these. You can do calculator if you want to. But I like to do fractions because it's usually a lot easier. So I just got a common denominator. So 1 over 20 is the same as 2 over 40. And then I move this 1 over 40 over here. So I've got 2 over 40 minus 1 over 40. And that leaves 1 over S prime. So 1 over S prime is 1 over 40. So S prime is 40. Pretty simple. Okay, now, the reason I already knew it was going to be 40 is because if you look at this, the focal length is 20. The radius of curvature is twice the focal length. And so it was going to be at 40. If you set an object at the radius of curvature, it will form an image at the exact same distance on the other, a real image at the exact same distance on the other side. So it's going to have an object at 40, you're going to have an image at 40. Okay, the other thing is magnification, lateral magnification is negative image distance divided by object distance. So it's negative S prime over S. So it's negative 40 over 40, which is 1, or negative 1. Okay, now, what magnification tells you, first of all, the S prime being positive tells me it's a real image. So that's my first criteria. Then magnification has two pieces. It has a negative and a positive, which if it's negative, that tells you it's an inverted image compared to the object. If it's positive, it tells you it's upright. Then once you're through that positive and negative, you ignore it and you look at this. If this is a number less than 1, it's a reduced image. If it's a number greater than 1, it's an enlarged image. And if it's 1, it's exactly the same size. So the magnification is 1. So if you put something at the radius of curvature, you get exactly the same size image, exactly the same distance away from the lens on the other side. That's only if it's at the radius of curvature, though. So don't think that's the way it always works. Okay, but magnification is minus S prime over S. So it's minus 40 over 40, which is minus 1. So minus is inverted. 1 means it's the same size. So I have a real inverted object or image that is the same size as an object. That's my 3 criteria. Okay. Now, I want to compare that to a similar problem, which is 46. Okay. So 46 says I have a 2 centimeter tall object, and it wanted to know the height of the object. I forgot to write that down. But the height of the image, since it's a magnification of 1, it's 2 centimeters tall because it's the same height as the object. But it would be a negative 2 centimeters because it's upside down, because it's inverted. So now I've got a 2 centimeter tall object that is 15 centimeters in front of a converging lens that has a 20 centimeter focal length. So I've got the same lens, I've got the same object, but now I'm at 15 centimeters. So now I'm inside the focal length. So now I know from those pictures that now I've gone to a diverging system and I'm going to form a virtual image. So let's see if the math backs that up. Okay, so 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. So 1 over 20 is equal to 1 over 15 plus 1 over S prime. My common denominator here is 60. So 1 over 20 is 3 over 60. 1 over 15 is 4 over 60. So 3 over 60 minus 4 over 60 is 1 over S prime, which is minus 1 over 60. So S prime is negative 60. Now, virtual images have negative image distances. So virtual images have negative image distances, and I got a negative number, so that's a good sign, so negative 60. Then I go to my magnification. So my magnification is minus S prime over S. So minus 60 over 15 is a plus 4. Plus means it's upright, and 4 means it's 4 times the size of the object. So 4 times 2 would be 8 centimeters tall. And it's positive 8 because it's upright. Okay? All right. Okay. So I'm going to stop the recording.